Good afternoon, my name is Juha and I'm a master student from Korea University in South Korea. Today I'm going to talk about RSMA-based Bistatic ISAC framework for LEO satellite systems. This is joint work with Jae-Hub Sung, Jae-Hang Ryu, Professor Lee Jae-Mao from Shanghai Tech University in China, and my supervisor, Professor Won Ji-shin. My presentation has 5 parts. First, I will introduce the motivations behind our work and explain the technical challenges we aimed to overcome. Next, I will briefly describe the system model and the pre-coder optimization process. Then I will show and analyze our simulation results. Finally, I will conclude with some remarks. A low Earth orbit satellite, in short, LEO satellite communications are getting great attention from academia and industries. LEO satellites operate at lower altitudes than conventional geostationary orbit satellites, so they can provide low latency and high data rate communication service. Furthermore, they can offer global and massive connectivity. Especially in recent days, researchers focusing on the full frequency viewed scheme. In this scheme, the same frequency bands are allocated to each beams and interference is managed by pre-coding scheme. So by doing so, we can improve the spectral efficiency. Meanwhile, integrated sensing and communication, as known as ISAC, is also gaining great attention. In ISAC, communication and radar function cooperate, avoiding resource competition. Recently, researchers have primarily focusing on the non-orthogonal ISAC, where the dual functions share same wireless resources. So thus, although these two technologies may seem to be independent, they share the same research direction, which is improving spectral efficiency. Therefore, it is very natural to combine both technologies to enjoy the synergy. So this is motivations of our work. Even though both technologies have been extensively studied independently, combining them is not simple. There are some critical challenges impeding this integration. First, there are general challenges in ISAC. Since communication and radar function share the same hardware and wireless resources in ISAC, interference is a key challenge. Here, intra-function interference refers to the inter-user interference among communication users, while inter-function interference refers to the interference between communication and radar functions. So effective management of this interference is one of the most difficult challenges. Next, we need to properly design dual functional signals, considering the conflict between uplink and echo signal. Furthermore, there are challenges arising from LEO satellites. As mentioned, LEO satellites have a lower altitude than traditional satellites, but the propagation distance of the signal is still very long. So this leads to severe path loss of the echo signal, making radar estimation infeasible under the limited power budget of the satellite in real world. Additionally, since the round-trip delay is very long and the velocity of the satellite is very fast, it is difficult to obtain instantaneous channel state information at the satellite. Therefore, we need to design a more flexible and robust ISAC structure and multiple access scheme based on these considerations. To address these technical challenges, we applied 2 key technologies. First, to manage both inter-function and intra-function interference, we employed RSMA. But I will skip the technical detail of RSMA here because I believe you are familiar with this concept. Next, to reduce the echo signal path loss and improve the feasibility of radar estimation, we employed bistatic ISAC structure. So as you can see from the figure, the monostatic structure means the radar transmitter and radar receivers are physically co-located. However, in the bistatic structure, these are physically separated. And so this is more generalized version of the monostatic structure. So why did we employ the bistatic structure? This slide shows the reason. As shown in the figure at the right side, there is a LEO satellite, a radar target, and a ground radar receiver that is physically separated from the satellite. In this scenario, we simulated the path routes of the echo signal in both monostatic and bistatic structure. So here the x-axis represents the altitude of the radar target and the y-axis represents the echo path routes. And the solid line represents the bistatic structure. The dotted line represents the monostatic structure. As a result, the bistatic structure experiences much less echo path loss compared to the monostatic structure. And this gap is significant when the target altitude is lower than 20 kilometers, while the realistic radar targets, such as drones and aircraft, exist. Next slide is a system model. As shown in the left figure, there is a LEO satellite, a radar target, K communication users, and the ground radar receiver. By employing the bistatic ISAC structure, our system model became geometrically complex but general. First, at the gateway, the K users' messages are split into K private streams and single common stream. Additionally, we considered a dedicated radar sequence only for the purpose of radar function. After linear precoding, the satellite transmits this superimposed signal to the K communication users and the radar target. At the communication user's end, the user optionally cancels the radar sequence and sequentially decodes the common and private stream. The radar receiver receives the signal reflected by the radar target and performs the estimation process to determine the radar target's location. This is channel model. Here G sub k is the channel gain between satellite and the K user. The vector A is the array response vector, and theta sub k superscript tx and phi sub k superscript tx are the angle of departure, in short AOD, of the K user. The next slide is bistatic radar channel model. Here alpha is the reflection coefficient that includes both the free space path loss and reflection effects. Specifically, reflection effects here involve the angle of incidence and angle of reflection and the radar cross-section of the radar target. Finally, the dual functional transmit signal X is modeled as large P times S, where large P is the precoding matrix and S is the signal vector. Here S sub R is the dedicated radar sequence and S sub C is the common stream, and the S sub 1 to the S sub K are the private streams. Based on this channel and signal model, we derived performance matrix for designing the joint precoder. First, the communication performance matrix is the upper bound of orbiting rate. Here delta sub SIC is at 0 if SIC is enabled and it is 1 if SIC is disabled. Here SIC means SIC of the radar sequence, not common stream. And this matrix does not depend on the instantaneous CSI, but depends on the geometrical and statistical information of the channel. The geometrical information means AOD of each user, and statistical information means average channel gain. And this information has much slower variation compared to the instantaneous CSI, which makes these are suitable for precoder design of LEO satellite systems. Next, for the radar performance matrix, we mathematically derived the Kramer-Rao bound, which is lower bound on the variance of any unbiased estimator. Using this performance matrix, we formulated the joint precoder optimization problem. The objective is to maximize the minimum achievable rate among all communication users. And first and second constraints are the Kramer-Rao bound constraints for radar performance. And third and fourth constraints are related to common rate portion. And the fifth constraint is limited power budget constraint. To address the non-convexity of our problem, we applied various relaxation techniques. But I will not explain this in detail due to the time limit. But if you have interested, please refer to our conference paper. And this is approximated convex optimization problem. Using the CVX toolbox, we can obtain the suboptimal prequarter through some iterations. Next, we analyzed the performance of our proposed framework. First, we will show the communication performance under various transmission modes. The x-axis represents the satellite power budget and y-axis represents the minimum rate, which is the objective function of our optimization problem. The red lines indicate the performance of RSMA, and the blue lines indicates the performance of SDMA. The dotted line represents the communication only mode, which of course shows the best communication performance. The solid lines represent the communication performance of ISAC mode. In SDMA, performance gain can be achieved by using the additional radar sequence and corresponding SIC. However, in RSMA, there is no such gain. In other words, we can say by using RSMA, it is possible to manage interference effectively, even without the additional radar sequence and SIC. This is the reason why RSMA is promising multiple access for ISAC interference management. To understand the details behind the previous figure, we also analyzed the transmission pattern and power allocation ratio. The red star represents the radar target, and the white circle represents the communication users. When the power budget is 20 dB watt, the common stream in RSMA and the radar sequence in SDMA use the majority of the power budget to form a beam towards the red target. Interestingly, in RSMA, no power is allocated to radar sequence. As we increase the power budget, the radar sequence in SDMA still form a beam only towards the red target. However, the common stream in RSMA form a beam not only towards the radar target but also towards the communication users. This means the common stream plays three roles in our framework. First, the common stream form a beam towards the red target. Second, it manages inter-user interference. Third, it manages the inter-function interference between dual functions. To conduct more practical research, we also performed the radar estimation. First, to estimate the AOA of the echo signal, we employed multiple signal classification algorithm, as known as music algorithm. And it was confirmed that estimation was better when the grammar about constraint was set more stringently. Next, although it was not included in the conference paper, we also proposed a joint delay AOD Doppler estimation algorithm. And the observation is consistent. For detailed information of the algorithm, please refer to the general version that will be published later. This is the concluding remark. The proposed bistatic Leo ISAC has been able to address various technical challenges. Intra and inter-function interference was effectively controlled using RSMA-based precoder. The dual functional signal was designed based on optimization. The conflict between uplink and echo signals was naturally avoided by introducing a bistatic structure. The severe path loss of the echo signal was also significantly mitigated by the bistatic structure. Finally, the difficulty in obtaining instantaneous CSI was solved by designing a precoder based on statistical CSI. And this is end of my presentation. Thanks for your attention.